When we hear music, then we hear a network of relationships. When we hear music, our brain perceives relations between notes and higher level entities. So, for example, the notes following each other form a melody, and the intervals between the notes, we perceive this relation as the melody. Notes that are simultaneous to each other we hear as a harmony. Smaller groups of notes we hear form a relation that form motives, and then we hear as a higher level process relations between motives. Or there's a relation between the rhythm and the pitch. In the algorithmic composition techniques we looked at so far, we generated parameters independently of another. So we generated, for example, first the pitch of some part, and then the rhythm, and then the pitches of another part. So it was relatively difficult. That's not impossible, but it is a bit difficult to define relations between parts this way. In this video, we will look at some composition technique that directly defines relations between musical objects like the note pitches and the rhythm of notes. And this approach actually goes back to an approach to teach and think about music composition that is centuries old. For centuries, music has been taught and has been reflected on using compositional rules. Rules describe how different parameters in the music, like for example the pitches in a sequence forming a melody, how these parameters are somehow related to each other, and how a certain musical style can be described by describing how these parameters are formed. In the composition technique and the algorithmic composition technique that we look at in this video, we are relatively closely mimicking what traditional music theory does by describing music with rules. We are having small computer programs that implement rules, and then there is another computer program that makes sure that when we generate music, all those rules are observed. In order to do that, we are using two PWGL extensions, two libraries, which we briefly looked at in the installation video. I'm just briefly reminding that we are having, if you haven't installed these libraries before, we are needing two libraries. One is the library cluster engine, and the other one is the library PWGL cluster rules. If you haven't installed them yet, you find them on the GitHub /t/cluster engine, and the other similarity on the GitHub /PWGL-cluster-rules. Make sure, and there's also another library called cluster rules without the PWGL up front. Make sure you take the PWGL cluster rules library, because only that is actually defined for PWGL. One little piece of caution: when we define patches using the library PWGL cluster rules, then the library, unfortunately, because of some implementation quirk I did, is not automatically loaded when you load the patch. So you always make sure that you have to load the library first. The reason for that is explained at the website I just showed you. But there's another way to make sure that that library is always loaded. In PWGL, you can autoload libraries under File, Autoload Libraries, you can make sure that some libraries are always loaded by just ticking their box here. And then whenever PWGL starts, that library is loaded. Don't load very, very many libraries, in particular not those libraries that you don't use anyway. That way, it will not only slow down the loading process. In case there's any problem with the library, you may have a problem starting PWGL at all. So only use libraries that you tried before and that you actually want to use. Now, let's start introducing just step by step how we can define a patch that uses compositional rules and generates music that follows those rules. We start, as we started in most of these videos, by saying we want to have a score as an output. Here is a score editor for our output. I make this already bigger in advance because I know that I will need some room available. And as a second object, once we have loaded the library, we use the box that gives the library cluster engine its name, and that's called cluster engine. Here we go. That's a box with lots of inputs. We will by and by explain what these inputs are. For now, it's sufficient to know that this box outputs the score. And so we will set there is the output. We will set that it outputs to the score. When we use a compositional approach that uses rules here, in terms of computer science technology, we are talking about constraints. We are restricting the output by constraints. With this approach, what we actually do is first we define a range of many possible scores, and then we restrict that range. We define basically our universe of possible scores, and then we define restrictions by applying rules. And then we randomly select one of the possible scores that's left. It's a bit simplified. That's not actually how the algorithm works, but you can think of it like that right now. And in order to first define the range of possible scores we have, what we do is we define the possible pitches and the possible rhythmic values for each individual part that we allow. That's done here in this lowest line. This, if I click on the title here, you see the name. I'll make this a bit bigger and you can better see that. The name of this input and that input is called rhythm domain 0 and pitch domain 0. This 0 stands for, we can later on have more parts, and then we have the rhythm domain of 1 and 2. Yeah, just remember that when we have an index, they always start with 0, so the first part is the 0th part actually. Removing those extensions then. Okay, so let's just start here by saying we allow for rhythmic values, namely a quarter standing for a quarter note and an eighth standing for an eighth note. And if we evaluate this box now, then we have just some random sequence of quarter and eighth notes. And we didn't specify any pitch yet, and therefore this is basically unpitched. Not very interesting, just showing you the idea. If I evaluate this a bunch of times, you see we have different random solutions, but we have no we have no rule yet restricting the output, so it's just random. Now I take back this eighth note. You see they are put there with double parentheses. There is a very good reason for that, which we explain in a later video. For now, just assume that that's the case. Let's say we want to write a little melody in C major. So for the possible pitches, we define the pitches of the C major scale. The pitches go in here. I could now enter them directly as I just did with the rhythmic values, but I'm introducing some box that makes it a little bit more easy to do that. And that box comes now from the library cluster rules. The library cluster engine defines the constraint solver, that is the program that searches for solutions, and ways to apply constraints to the score. The library cluster rules, by contrast, predefines a range of rules and also some utilities. And now we are using one utility that is called scale the pitch domain. I should perhaps mention acknowledgement. The library cluster engine has been defined by Elgin's 100, and then I defined cluster rules to expand that. Scale to pitch domain is an utility that allows us to define the pitch domain for a certain scale a bit more easily. Just reshape this a bit. Let's say we want to have a melody in C major, and for that we allow for the pitches of the C major scale. The C major scale, C, D, E, F, and so on. As MIDI note numbers, we can express that with, if we take the middle octave, 60, 62, 64, 65, and so on. But we can also express that a bit more generic by pitch classes. Pitch classes are pitches without an octave component. And there, C is actually 0, D is 2 semitones higher, 2, E is 4 semitones higher, 4, and so on. So I'm entering now the C major scale here as pitch classes. C, D, E, F, G, A, and B. And additionally, I said, yes, the C major scale, that can happen in the middle octave, means between C4 and C5, but we could also set this into some other octave, or does not necessarily need to start at the C. Let's see, I want to start with this melody, not at C, which would be middle C, but instead at something a bit further down. And this would be C4, C5, 72. Let's allow this for a little bit higher. 76 is E above, the octave above middle C. This box now generates a range, a domain of pitches, the pitches that we allow for in our solution. Remember, if I evaluate the box, it shows here at the bottom end of the patch. And there we see 55, 57, 59, and so on are the pitches up to 76. Each of these pitches again wrapped in a separate parenthesis. This format is therefore a good reason that we explain a bit later, but because of this format, it is a bit more easy to enter that with this auxiliary box. So let's say, okay, now we have the pitches of the C major scale in the range of, a certain pitch range, and we have only notes that are quarter notes, crotchets, and evaluate this, and I get some random sequence of pitches. Okay, you might find, this is just a random pitch sequence. All the pitches are in C major, yes, but it's not exactly a melody because the pitches just skip around wildly. In a melody, the actual intervals between the notes are more controlled. They are not skipping around wildly like that. So, how do we address that? We add a rule that restricts the intervals between the pitches. And so now we start doing actually proper music constraint programming using a compositional rule. Under cluster rules, you find we have several menus with various rules already predefined. And I'll start with this one, under cluster rules, melody, min, max, interval. I expand the box, remember I press plus, make it also a bit bigger so that we can actually see this menu here properly. Pull this over. And yeah, so I can select a number of possible arguments. I want to set for the rule, I want to set the maximum interval. And now I enter this as a rule. The cluster engine gets the rules input there. Let's say I want to restrict melodic intervals to a major third at most. I just set this to 4. I reevaluate this, and suddenly we have lots of pitch repetitions. Actually, not we have some pitch repetitions and some steps. So the result is still random to an extent, but it is only random as long as it follows this rule. Such an output we could also generate without rules by generating a melody where we always control simply the interval. But here we are, as we see, rather flexible, that we have later more than one rule, and that would be more difficult using another approach. Yeah, just let's have another solution. So perhaps we don't like these pitch repetitions. We could disallow pitch repetitions by, again, expanding this box. Just to make it a bit more easy to read here, and set that the minimum interval should be 1, not 0, but 1, so at least there is a semitone, yeah, so that disallows all pitch repetitions. Now you might feel, okay, this sounds all rather blunt, and one reason why this sounds rather uninteresting is that the rhythmic values are all equal. How about making the rhythm a bit more interesting? And for that, we just allow for a second rhythmic value. I enter an 8th note here now. Hold on, did I actually enter some? I hope that's all right. So now I have a random rhythm of either 8th notes or quarter notes. You see, I can just generate multiple results. That's why if I play this, it has a tendency to have lots of syncopations, yeah, that the longer note is actually crossing beat boundaries. Yeah, here is another syncopation, here's another syncopation. Yeah, it's not necessarily, but it can happen. Yeah, here again are syncopations. So what you could do always is generate so often a new result that you find something where you feel, yeah, this is not what I like. Or you add another rule to further restrict the output, that you say, in this case, for example, I want no syncopation, or at least I don't want to have two syncopations following each other like this, because that clouds a bit the rhythmic clarity. So let's have another rule, in this case a rhythmic rule, under cluster engine rules, under cluster rules rhythm. There is, for example, a rule called no syncopation. There's also a rule called no two consecutive syncopations. Let's use that for now. I just move those boxes a bit around. Now, if we would enter this rule here, then you would see, oops, I can have only one of them. So I need some way to enter more than one box. And for that, we have the box cluster engine rules to cluster. That's a box that can be expanded as much as you want. Move everything up here a bit to make some room. And yeah, I'm just entering some rules here. I can leave actually out some rules. There are some slots in case I want to have added something later. And if I evaluate this box now, that gives me a list of rules. Yeah, in this case, we just have 2 rules. Evaluate the box, the result, and now, hey, we have still 2 consecutive rules. 2 consecutive, 3 consecutive. Something happened here. That is of course, we forgot to connect cluster rules to rules and the rules input. There you go. Just let's re-evaluate this again. And now syncopations are more controlled. Yeah, you might find, okay, that's a start. That sounds perhaps not too bad as a little melody. How about we want to expand this example and have 2 melodic lines have some counterpoint, some harmony. For that, I expand this box. Now I have 2 parts. And for both of these parts, I need to define the rhythmic, the rhythmic domain and the pitch domain. Yeah, remember, rhythm domain and pitch domain. So I could simply copy this and paste it over here if I want to have the same rhythmic possibilities for both parts. We could do the same with the pitch domain, but instead what I'm doing is I copy this box. But now I very slightly change the values, and we say the upper part should be a bit higher, and the lower part shouldn't be going up as high. Now, if I re-evaluate this, then we have 2 parts, but unfortunately the score editor does not by default show more than 1 part, so I did right-click into the score editor in order to bring up this box, and then I can set the number of parts it allows to show. Now if I re-evaluate the score editor, then we have 2 parts. Just moving this around a bit with my trackpad. If I play this, then you hear the harmony is pretty random. It's all in C major, but otherwise it's random. But also the first part follows our rules that we specified before, but the second part, you see, does not. Yeah, we have still these large skips. We can have probably syncopations. There we have 2 consecutive syncopations. In order to have those rules followed by the other part, we need to somehow change that. What we can set here is, if I click on the name, you see that the first input here is called voices. That specifies for which voice this rule is applied, to which voice this rule is applied. And 0 means it's the first voice. If I set this to 1, and likewise the voice of this to 1, then the lower part now follows that, but the upper part has all those skips. There's another way to apply it to both. Whenever we have a rule that has the argument named voices in plural, not voice, but voices, and we actually can give it a list of 2 or more voices. If I evaluate this box now, then you see it actually outputs 2 rules. One for each part. It just does that because I set this here to 2 inputs, 2 voices. Now if I evaluate this, our admittedly very simple melodic and rhythmic rules are followed by both parts, but still in terms of harmony, they clash a lot without any further control. Yeah, so dissonant and consonant intervals just follow each other randomly. How about we develop this example further by adding a harmonic rule? I go to cluster rules, harmony, and now I add some harmonic rule. For example, this one, set harmonic interval. Set harmonic intervals specifies specific intervals that are allowed or disallowed between certain parts. And in this box, if I show, you see the first argument is voices, the second argument is intervals. Voices are already set to our first 2 voices. Intervals I'm setting now, and the other arguments we can explain at another stage. Let's say I'm allowing for all the arguments that are consonant in traditional counterpoint. That goes back now, these rules, a couple of 100 years in Renaissance counterpoint. That's about 500 years ago. Compositional rules harmony was controlled by controlling the intervals between consecutive notes. And that's basically what I'm doing here. At a later stage, we can control some underlying harmony, making it a bit more advanced. But for now, just to get started, let's take that as an idea. So we allow, for example, for 0, that means unison, both voices have the same pitch. And 3, they can be a minor third, major third, not a fourth, but a fifth, and a minor 6, and a major 6, and perhaps an octave. If I evaluate this now, hello, I didn't connect it. If I evaluate this now, then you hear, indeed, now all the beat onsets are consonances at notes that are not on the beat, like this one. Yeah, the first 2, they are consonant, but the second 2, if the second one in the second voice you hear is dissonant. If just play the beginning again. Yeah, so that is consonant, the second is dissonant. If I want to make sure every note is consonant, I can change the setting here, setting it to all. Other settings here allow. This means beat means every note starting on a beat, and this is every note on every first beat in a bar, and there are some others. So let's say that we set this to all notes, and now everything is consonant. So there you have it. We have a first patch that defines some simple, somewhat traditional counterpoint. There would be now very many ways to expand and change this patch. First of all, we can change the settings of rules. Yeah, you saw I set, for example, the minimum and maximum interval here, or the parts. Yeah, we can, for example, say that we only want to have imperfect consonances. So we don't want to have unison, that's the same part. Both voices have the same pitch, or no fifth and no octave. Yeah, only the more sweet sounding, imperfect consonances, that's minor and major third and minor major sixth. But if we do this, we might get at an over-control situation. Yeah, in this case, you see there are lots of voice crossings. Yeah, so, for example, basically what we are having here is that it sounds as if there are no repetitions because these voices basically just swap. That's a rule. If you don't want to have that kind of situation, we can, under counterpoint, say we want to have no voice crossing. And just connect the rule. Specify for which parts this rule, to which parts this rule is applied. Sorry, I meant to have 0 and 1. For clarity, I moved this patch quad a bit. And now we won't have such voice crossings. I'm a bit surprised that we have a fourth here. If it should actually be disallowed. This was unconnected. You see, okay, not sure why that happened. Let's do this again. Yeah, so there's now a tendency, because we have only very small intervals, that the parts go very much in parallel. Yeah, we could revise this further in order to allow this for more flexibility. Yeah, you see, I can just by and by spend more and more time to revise this. For example, I could take this over and use another rule instead, where I say, as a melodic rule, I'm not using min-max interval, but instead I use set intervals, where I specify certain intervals that are allowed. Make this a bit bigger so you can better read the input. It's all further down so that I can reach you. This specifies the intervals we allow. The melodic intervals, yeah, this is harmonic intervals. That means the intervals that sound simultaneously. This is melodic intervals, that are the intervals that sound one after the other. Let's say there we allow for a semitone, for a whole tone, for a minor third, a major third, and a fourth, not a tritone, but a fifth, and an octave. So that allows now for a bit more melodic flexibility. Yeah, before we allowed only for minor second to major third. Now we allow for larger intervals as well. And let's specify this is for the voices 0 and 1 again. I'm just double checking whether voices intervals. They are still rather parallel, but that's just by chance. It does not necessarily need to be like that. But works. But you get an idea, yeah? So we could do further changes, like, for example, we change the whole scale we use. Yeah, so far this is all in C major. Let's say we don't want to have C major and want to instead do a piece in D major. So what we can do is, now I'm using actually the same domain for both parts, because then I only have to do this operation here once. Use that input. And this now goes in here and there. So we have the C major scale, and for every note in the C major scale, we add 2. That transposes all pitches in the C major scale up 2 semitones, and we have D major. Yeah, I can again perhaps slightly expand the range here to make sure there's enough room for both parts. And if I evaluate this, you see, or we want to generate more notes in this box in the top right, top left corner. We control how many notes we generate. Actually, it's a bit oversimplified to say how many notes it generates, but that roughly is what it does. How many notes? And you might feel this is all in only consonant, and that's too simple. And we want to also allow for dissonance, but control how dissonances are treated. That's all possible, but I think I stop here. This library allows for a lot of compositional freedom by using various rules we have here. And if this is still not enough, then you can actually define your own rules from scratch by using those boxes. So just to summarize, when we listen to music, we listen to relations between simultaneous notes, between consecutive notes, between small groups of notes. And with constraint programming, with music constraint programming, we are able to control relations between notes by going back to a very old concept using compositional rules, applying compositional rules to music.